This is a question on ordinary and extraordinary polarized rays. So let us first look at the question, then we will draw the diagram and then we will try to understand. So the question says, two orthogonally polarized beams each having wavelength of 0.5 micrometer are incident on a two prism assembly. We will draw the diagram, then it will become clear. On a two prism assembly and emerge along the x-axis the prisms are of identical material and NO and NE are the refractive indices of the O ray and E ray respectively. So this is the question. Let us draw the diagram, only then this will become clear. So we have a two prism assembly so this is the first prism, this is the second prism. Then this is the optic axis for the first prism and optic axis for the second prism is in the plane of the screen. This one is the first prism. Optic axis is coming out of the plane of the screen, perpendicular to the plane of the screen, and this is the second prism. And the optic axis of this is in the plane of the screen. So let me just draw a line like this. Or maybe I could draw with a different color so that it does not get mixed up. So this is the optic axis for the second prism, this is the optic axis for the first prism, and the axes are as follows. So this is the x-axis, this is the y-axis. So the optic axis of the first prism is along the z-axis, and for the second prism it's along the y-axis. Then we have two orthogonally polarized beams. Let me choose different colors for the beams. So let me draw the two rays. both the rays, means there are two rays here, there will be two rays, two orthogonally polarized beams, but both of them would finally exit along the x-axis. That is what it has been written. So finally the ray is going to come out along the x-axis. So we can draw a normal at this point. This is the normal. Normal to the given line, to the given interface that we have. And the first beam is coming like so. Maybe a little bit better I can draw. This is the first beam. Then the second beam that we have, let me take another color. This will come somewhat like this, and then again move along the x-axis. So we have these two rays, and let me draw the polarization. So this ray is polarized, the green ray is polarized perpendicular to the screen, and the red ray is polarized in the plane of the screen. And let me draw what theta and phi are. So the angle that this green ray makes with the normal, this angle, this is our theta, and the angle that the red ray makes with the normal, this angle is phi. And also we are given the angle of the prism. So this angle is 30 degrees. So we have the two beams. This is the first beam, this one is the second beam, and they are orthogonally polarized as shown in the figure, and they both exit along the x-axis. So this is the diagram that we have. The question says, the question has two parts. Find the value of theta and NE. The second part is, if the right hand side, the right prism or second prism in our diagram starts sliding down with the vertical component of velocity what would the minimum time be after which the state of polarization of the emergent beam repeats itself. So let us understand what this question is all about. So in this question we have two prisms placed like this as shown in this diagram, and the optic axis of the prisms are shown in this blue. So for the first prism, the optic axis is perpendicular to the screen. For the second prism, the optic axis is in the plane of the screen along the y-axis. Then we have two rays, the red one and the green one, which are orthogonally polarized. Red one having polarization in the plane of the screen, green one having polarization perpendicular to the screen, and they both hit the interface of the two prisms and then finally emerge along the x-axis. So this is the setup that we have, and we are supposed to find out the value of this theta and NE being the refractive index for the extraordinary ray. And then in the next part it says that the second prism, this prism, starts sliding along this interface to come down, and then we are supposed to see what happens to the state of polarization and when does it repeat. So let us start solving these parts one by one. Let us look at the first part. So the first ray that we have drawn in red, this ray is propagating as an O ray in the first prism. So this first ray is O ray in first prism, and it will be an E ray in the second prism. Why so? Because the polarization is perpendicular to optic axis. In this case, the plane of polarization is perpendicular to the optic axis for the first red ray, and for the second ray it will be an E ray in first prism, and it will be an O ray in second prism. Again, this is because in the first prism, for the second ray, the polarization is parallel to the optic axis, so it will be E ray, and when it moves to the second prism, the polarization is perpendicular to the optic axis, so it will be an O ray. And also we are told that the material of these prisms is calcite, and in calcite we have the following: NO is greater than NE. So if we look at the first ray at the interface, so the first ray will bend towards the normal. Sorry, I said the wrong thing. First ray is going to bend away from the normal, and second ray is going to bend towards the normal. As we have rightly drawn in the diagram, we see that the red ray is bending away from this white normal, and the green ray is bending towards this white normal. This is because of this NO is greater than NE. So for the first ray, it propagates as O ray in the first prism over here, and since NO is greater than NE and the first ray is an E ray in the second prism, so for the first ray it appears as if it is moving from denser to rarer. So from first prism to the second prism, for the first ray is like it's moving from denser medium to a rarer medium, and for the second ray it is an E ray in the first prism and becomes an O ray in the second prism. So it is as if it is moving from a rarer to a denser medium, because NE is less than NO. So for this case, this is like E ray going to an O ray. So and Ne is less than No, so it is as if it is rarer to denser. Here this is O ray becoming an E ray, so it is as if it is going from denser to rarer. So the diagram that we have drawn clearly shows which one is bending towards the normal, which one is bending away from the normal. Now we can apply Snell's law to each of these rays at the interface. And before that, let me write down this angle. So this angle right here, this angle is going to be again 30 degrees. And why so? Because we are given that this angle is 30 degrees, so this angle will be 60 degrees, as this forms a right angle. This thing right here is a right angle, and if this angle is 60 degrees, we will have this angle as 60 degrees, since this is also parallel to the x-axis. So these two lines are parallel and they are parallel to the x-axis. So from that we have this angle as 60 degrees, and this is a normal, so this angle is 90 degrees. So this angle has to be 30 degrees. So the angle that the emergent ray makes with the normal is 30 degrees. So let us apply Snell's law to both the rays. For the first ray, we have it is ordinary ray in the first prism, so NO sine phi, phi is the angle with the normal. It becomes an extraordinary ray in the second prism, so NE sine theta, theta is the angle made with the normal. This is for the first ray. For the second ray, the second ray is an E ray in the first prism, so NE sine theta, it makes angle theta with the normal, and it becomes O ray in the second prism, so we have NO sine theta, sine 30 degrees. So this comes from using Snell's law. Snell's law we have seen in some of the previous videos. This is for refraction at any given interface. Now we will use these two relations to basically solve for theta and Ne. Since there are two unknowns in this theta and Ne, we are given what the value of NO is, and we have the relation of phi with theta. So let us try and simplify these two relations. So from the first relation, we have the following: Ne sine 30 degrees is equal to NO sine phi, and sine 30 degrees is half, so we have Ne by 2 is equal to NO sine phi, and NO we are given, this is root 3 plus 1 by 4, so this is root 3 plus 1 over 4, and sine phi we know in terms of sine theta is given as the sine theta by 3, so sine phi is sine theta over 3. So from this we get Ne in terms of sine theta as follows. So this is Ne in terms of sine theta, and from the second relation, we have NO sine 30 degrees is Ne sine theta. So from here we get sine theta. First let me write down the value of sine 30 degrees. This is half, so NO divided by 2 is equal to Ne sine theta. So this gives us sine theta is NO over 2NE. Now NO we are given is root 3 plus 1 over 4. It is given in the question. This is NO, and then divided by 2 and then divided by NE. NE we will use from here, from this relation. So from here we will use the NE value. So divided by NE would be basically so this gives us sine theta is, let us simplify some of these terms. Root 3 plus 1 cancels out. This 2 cancels with this 6 to give 3. So sine theta is 3 divided by 4 sine theta. So this gives us sine squared theta is equal to 3 by 4. So sine theta is root 3 by 2, which implies theta is equal to 60 degrees. So we have solved for theta. Now from this we will come to know NE again by using this relation out here. So let us do that. So we have NE is root 3 plus 1 over 2 sine theta over 3. Theta is 60 degrees. So this is root 3 plus 1 by 2 sine 60 degrees over 3. And sine 60 degrees is root 3 by 2. So this is 3 plus 1 over 2 times 1 by 3. Sorry, not 1 by 2. Times 1 by 3 times root 3 over 2. So let us try and simplify some terms. So this is 1 over 4 root 3 plus 1, and this 3 and root 3 will give us a root 3 in the denominator. So this gives us 1 plus 1 over root 3. So this is the value of NE that we were supposed to find out. So this right here is NE, and we have completed the first part in which we were supposed to find out value of theta and value of NE. Theta being this angle that the second ray makes with the normal. Now let us move to the second part. So in the second part, the second prism is sliding downwards along the interface. So let us draw the diagram for that. This is part B. So we have this two prisms put together, and then the second prism starts sliding downwards. This is first prism, this is second prism. Now this prism starts sliding. So when it starts sliding, we get the following situation. So the second prism would have it would slide down and come to a position like this. Like this. So the prism, the second prism we are given, has a vertical speed uy, and it would also have a horizontal component of the speed ux, because if only the vertical component is there, the prism would just fall down and it would not be able to maintain contact along this interface that we have. We need to maintain the contact along this interface. If only the vertical component of the speed is there, then it will lose contact, because then we will come to a situation somewhat like this. Only vertical component of the speed is there, then it would lose contact. So we don't want such a situation. This is not what we want. We want the contact to remain intact. So there will be a vertical component of the speed as well as a horizontal component of the speed. And we are given the vertical component of the speed uy is 1 micrometer per second. So we need to find out the horizontal component of the speed as well. That can be found by simple trigonometry. We were given that this angle is 30 degrees. So that means that this angle is 60 degrees. So this angle right here is 60 degrees. So we know that uy over ux will be tan 60 degrees. So the net velocity direction would be along the interface. The net velocity direction would be along this interface that we have, and the components are uy and ux, and this angle is 60 degrees. So this angle right here is also 60 degrees. So we have uy over ux is equal to tan 60 degrees. And tan 60 degrees, oh sorry, let me change the color. Tan 60 degrees is root 3. So we have ux equal to uy over root 3. Now we have the rays emerging along the x-axis. So we have this as our emergent ray. This is the x-axis. This horizontal is the x-axis. So our rays, both the beams, are finally emerging along the x direction. And let us consider that this distance right here, the distance that the rays travel in the second prism, let us call this distance d. So path difference between the ordinary and extraordinary rays, path difference between the ordinary and extraordinary rays is as follows. This is because the ordinary ray will travel a distance d, extraordinary ray will also travel a distance d in this second prism, and the path difference between the two rays would be given by the difference in the optical paths, and difference in the optical paths is refractive index times the path traveled and subtracted with the extraordinary term. So NO minus NE times T is the path difference between the O ray and the E ray. So this is path difference between O ray and E ray after it has traveled inside the prism and then when it is exiting the face of the prism. Now this path traveled inside the second prism, this D will be a function of time because the second prism is sliding downwards. So this D will change as a function of time. It will reduce with time, so to say. So let us say initially if we had a distance D naught, then after certain time T, it will become D naught minus Ux times T. This is the distance that the rays will travel after a certain time T. So let us say initial path difference between the O and E rays is going to be as follows. And then after time T, the path difference would be as a function of T so the difference, the actual difference between these two path differences would be as follows. Now we know the relationship between phase difference and path difference. So phase difference is given as 2 pi by lambda times path difference. So phase difference is equal to 2 pi by lambda into the path difference. So initial phase difference, if we write down, let us say delta naught, initial phase difference would be this, and after time T, the phase difference would be as a function of time as follows, and the difference between these two phase differences from t equal to 0 to some time t would be which in turn would be from this expression right here. So this is the phase difference that we will get after some time t. Now for polarization to repeat itself, because that is the question, we want to find out when the polarization state repeats itself. The condition is that this delta should be equal to pi. And why so? Simply we can see, let us say for example, if we have linear polarization, let us say we have linear polarization like this, then after a rotation of pi, after pi, we will again get the same linear polarization. Again it will return to its original state. In between it will be in some other direction. Let us say it will rotate, it will come here, then it will further rotate, and finally at pi we will get the same orientation for the linear polarization. Similarly we can see for elliptical polarization also. If we start off with, let us say, some elliptical polarization like this, then it will rotate first, it will rotate, and then it will rotate, keep rotating, and after pi it will again come back to its original state of polarization. So for polarization to repeat itself, we have this condition that delta should be equal to pi. So let us set it in the expression for delta. This should be equal to pi for repeatability of the polarization state. So from here we will find out T is equal to lambda over 2 n0 minus ne times ux. So at this, after this time, the polarization state would repeat itself. So we can find out the value of this because we know the value of each of the other terms. So let us first find out NO minus NE. So NO is, we are given root 3 plus 1 over 4. NE we found out in the first part A. So NE was this. We had found out NE in the first part. Just to recap, here NE is there, 1 by 4 into 1 plus 1 over root 3. So this is NE. So let us simplify. So this is the value of NO minus NE, and UX we had found from trigonometry is UY over root 3, sorry. So let us plug in the values. T is lambda over 2 NO minus NE UX, which is lambda over 2. NO minus NE is 1 over 2 root 3, and UX is UY over root 3. So this 2 right here would cancel. So this would give us lambda over UY into 3. And we know the value of lambda we are given is 0.5 micrometer. So this is 3 into 0.5 micrometer, and UY we are given is 1 micrometer per second. So this is 1 micrometer per second. So this is 1.5 seconds. So after 1.5 seconds, the polarization state will repeat itself, and the next time when it repeats can be found out from here. So polarization would repeat itself at pi, then at 2 pi, at 3 pi, at 4 pi, and so on and so forth, basically integral multiples of pi. So the next time at which it will repeat would be 3 seconds, and then 4.5 seconds, and so on. That is, it will go in integer multiples of 1.5 seconds. So this solves the question. In this question, the takeaway was how to deal with ordinary and extraordinary rays in any given scenario. So we had two rays over here, ordinary and extraordinary rays. These two rays were orthogonally polarized, and then we saw whether it will be an O ray in which prism and an E ray in which prism. So when the polarization is perpendicular to the optic axis, then that is O ray, and when polarization is parallel to the optic axis, that would be an E ray. So this completes the question.